Welcome to our next video. So in this video, we're going to be discussing atomic theory. Good news, this is technically a review from grade 9 as well too, but you're going to see this is in much more detail than anything that we covered in grade 9. So we're going to talk about the atom that we know today and how it came to be. Now we're going to focus on this word theory. We talked about theory before when we talked about the scientific method, and remember, a theory is really just a best guess. So again, what I want to do is I want to go through parts of the scientific method, and essentially I'm going to be discussing what was wrong with each of the theories, the mistake in each of the theories, and how that caused us to seek out the next theory. So we're going to kind of take a trip back into history, and we are going to start with our friend Democritus. So Democritus was actually a Greek philosopher. He wasn't necessarily just a chemist. At that time, you didn't necessarily study just one branch of science. You studied several. So Democritus studied chemistry along with other things. He worked along with this gentleman called Leucippus. And what Democritus and Leucippus said is that matter cannot be divided indefinitely. Essentially, it's the idea of a piece of paper, right? If you have a piece of paper, you can tear the paper in half, you can tear it in half, and eventually you're going to get to paper pieces that are so small that you can no longer tear them in half. So Democritus and Leucippus said that matter cannot be divided infinitely. So based on that, they proposed the idea of an indestructible, indivisible particle. They called these atomos, and then we later shortened it to atoms. So they didn't describe what that particle looked like at all. They just said that everything is made up of very, very tiny, indestructible, indivisible particles that eventually you can't get any smaller. This school of thought lasted for quite some time because that's exactly what it is. It was a school of thought. So the issue with Democritus's theory is it really kind of lacked any evidence, right? We didn't have the tools to actually study science at that point. It was a theory coming from a philosopher. So while it was a great idea, we couldn't prove or disprove it. Then John Dalton came along. That was in about 1803. And this is the first modern theory of the atomic theory history line. So he was a chemist, he was a physicist, and he was a meteorologist. And Dalton had some knowledge of chemistry. So he proposed what we call the billiard ball model. So again, you might remember this from grade 9. If you don't remember what billiards are, billiards is like a fancy name for a pool. So pool, if you picture like a pool ball, you can picture like a nice solid sphere. So some people actually call Dalton's model the solid sphere model. So it's a billiard ball model or the solid sphere model. This is grade 11 chemistry, so we have a couple more points that surround this. So we actually have 5 points that we discuss in grade 11 chemistry around Dalton's theory. Now, these points were actually linked to what Dalton knew about chemistry at the time. So if you notice, the first point is actually very similar to what Democritus and Leucippus said, that all matter is made up of tiny, indivisible particles called atoms. So he actually didn't disagree with Democritus or Leucippus. He agreed, but he wanted to add his spin, what he knew about science at the time. He said that atoms cannot be created or destroyed, so that goes along with indestructible, which is similar to Democritus and Leucippus. He went further though, because now we'd actually discovered elements. So he said that all atoms of a particular element are identical. So for example, all gold atoms look like gold, all silver atoms look like silver. So all atoms are identical. So this theory, this went ahead and said that there actually are different types of atoms, right? The different elements are made up of different types of atoms, so atoms can look different from each other. At this point, we knew that compounds could exist. So he said that compounds are formed through the combination of elements. So you're going to have your 2 different atoms. Let's say that you have a gold and an oxygen atom. He said that a compound can form when you take that gold and you take that atom and you go ahead and you combine them together. So a gold and an oxygen atom can combine together to make the compound gold oxide. So he knew compounds could exist, and he used this theory to explain how compounds came to be. Next step is based off of this step, and it says that chemical reactions involve atoms recombining to new substances. So chemical reactions are going to involve 2 atoms, they're going to recombine, and they're going to form a new substance. This point right here is actually the issue in his theory. So we want to remind you of what a billiard ball looks like. You have this kind of solid sphere, right? So you have this solid sphere here. Let's say that this here is hydrogen, and let's say that this is oxygen. So Dalton's theory was that these two solid spheres should be able to go ahead and recombine to form a new substance. The issue is he didn't propose any way that they can actually recombine. You have two solid spheres and you're just kind of smashing them together. So how are they actually going to go through and form a new compound? So this was kind of the limitation of Dalton's theory. So since it had a limitation, that means that another theory must have been developed. It was about 100 years later, and that was from J.J. Thomson. So J.J. Thomson wasn't necessarily actually studying chemistry at all. He was actually studying these cathode ray tubes. So they're like a high energy picture, almost like a laser, not really a laser, but a high energy beam of light. And he noticed that there's strange beams that actually were evacuated from the glass cathode ray tube. So he noticed this kind of strange beam of light, or this strange beam of energy that was coming out of the cathode ray tube he was studying. So when high voltage is applied across that cathode ray tube, fluorescence is produced from an invisible beam striking a zinc coating. So he again noticed kind of like a bright flash of light being produced from this cathode ray tube. So he knew there was some sort of energy existing in that cathode ray tube. So his conclusion was that those cathode rays must consist of tiny particles. So again, it looked like a tiny little light. So those cathode ray tubes must have tiny little particles in them. He said these charged particles were much smaller than the tiniest atom. So he got some inspiration looking at these cathode ray tubes and said, well, these must be made of particles, but these particles must be much smaller than atoms. So he was the first one that said that there must be particles that are actually smaller than atoms. That means that these particles must exist from within atoms. And he even went as far to suggest that those particles were coming from the metal electrode. So they were coming from the metal electrode within the cathode ray tube. So he dubbed these particles subatomic. Remember, sub just means smaller than. So he's saying there's a particle that's smaller than an atom. So he's saying that particle must be subatomic. So he was the first one to propose subatomic particles, particles within the atom. We later called those particles electrons. So he actually, by looking at the cathode ray tube, was actually observing electrons. So you actually know a little bit about electrons from grade 9 electricity as well too. We know electrons flow in a circuit and they leave from the metal side, right? They leave from the negative side. So he was actually watching electrons flowing from the metal electrode, and he was the first one to observe subatomic particles. This led to what we call the plum pudding model. The plum pudding model says that an atom is made up of at least one type of subatomic particle. So let's take a look at what this subatomic particle might look like. This is Thomson's proposed plum pudding model. So he said that the atom, which is this light purple here, is actually mostly loosely packed positive space. He calls it the positively charged pudding. So it's kind of like if you've ever seen plum pudding before, it's like a loose kind of pudding here. And within that pudding, there was little densely packed electrons. So within that pudding, you had these negative electrons that were scattered throughout this positive. So he said that we actually can have electricity be conducted, and electricity is actually conducted when these negative subatomic particles actually leave the atom and flow through a circuit. So he was actually knew about electricity. He was able to go ahead and figure out how a positive ion was being formed based off this model. So this model actually answered a lot of questions that we had in chemistry and physics in the time. Notice that he knew that an entire atom does have a neutral charge. So that means that there must be positives that balance out these negatives. So the actual particles themselves, he said, were negative, and the rest of the atom was just made up of positive space. Well, J.J. Thomson was making that observation. Rutherford worked on the nuclear atoms. So, just a little bit of a background information about Rutherford and what was going on at the time. Rutherford worked with the Curies, and he led to the discovery of strange beams called radiation. So, he was actually basing his research off of the Curies, and he was looking at radiation. So, Rutherford actually discovered that radiation comes in three different forms. It comes in the form of an alpha ray, which is positive radiation, a beta ray, which is negative radiation, and also gamma rays. You might remember gamma rays from grade 10 physics. So this radiation actually comes from the spontaneous disintegration of unstable atoms called radioisotopes. We're actually going to talk about isotopes more in our next lesson. So you'll learn a little bit more about what an isotope is. Biggest thing for this is I want you to understand that now we know about different types of radiation. So before, the only way for us to study negatives were based on those cathode ray tubes. Now we have a way to actually study positives, and that's based off of this alpha radiation or this positive radiation. So Rutherford is actually going to study this positive radiation here. This led to Rutherford and what we call the gold foil experiment. So you probably remember talking about this in grade 9. It's a pretty great experiment. So I'm going to go ahead and I'm going to dissect it a little bit further. So Rutherford was again using that beam of alpha particles. So remember that beam of alpha particles is positive. He said that that beam of alpha particles should have enough energy to pass through a thin piece of gold foil. So he had a little tiny thin piece of gold foil, and he was shooting these very high power particles at this thin piece of gold foil. He said that that should be enough energy to actually pass right through the thin piece of gold foil. How would he know that the alpha particles passed through the gold foil? He had a zinc sulfide screen that was actually set up behind that would pick up that radiation. So he could actually see if the alpha particles were passing right through the gold or whether or not they were getting stopped. The cool thing about this experiment and why we spend so much time on it is the first time he did this experiment, it actually seemed to work. So the experiment actually seemed to confirm the plum pudding model, which is what he was trying to do. He was trying to say, is the atom made up of mostly empty space, mostly that positive, loosely packed area with those negatives throughout? So it did seem to go ahead and confirm that the atom was a diffuse or spread out positive sphere. So this is what actually happened with the gold foil experiment. So again, when we first did this experiment, it seemed to go ahead and prove the plum pudding model. So again, he had that radioactive source, and that radioactive source was actually emitting those alpha, those positive particles, and they were passing through the gold foil. So when he did this experiment at first, he noticed that for most of the time, the alpha particles were passing right through the gold foil and was being picked up by the zinc sulfide beam. Now, this is actually where Rutherford's experimental design comes into play and how genius it is. Because Rutherford, even though he was expecting one thing to happen, he was ready for the unexpected. So when designing this experiment, he was expecting most of the alpha particles to pass through. So if you're expecting most of the alpha particles to pass through, most scientists would have set up a screen just right behind here. Instead, what Rutherford did is he actually set up almost a full 360 screen. Even though he wasn't expecting alpha particles to go anywhere but here, he set up a full 360 screen just in case. And it's a good thing that he did, because he found that if he did this experiment enough, there would be the odd time that we would actually have an alpha particle would be either reflected or deflected. So deflected means that it kind of shot off at a weird angle, and reflected means that it actually bounced straight back. So this was unexpected, right? He expected the particles should be able to pass through, and then he found that several of the particles actually didn't pass through. They actually were reflected or deflected, almost like they hit something solid. So the expected result, again, that Rutherford was expecting to see was particles should pass right through. And what he found is that most particles passed right through, but some were either reflected or deflected like they were hitting something solid. So again, just goes to show how persistent Rutherford is. 1 in 8,000 were actually anomalies. So that means 7,999 went through exactly like he expected, and 1 in 8,000 particles were actually deflected back. So think about how many times he must have done this experiment, and think about the fact that he actually recorded these anomalies. So anomalies can be very important in terms of telling you important information. So Rutherford went on to ask why, and he was able to make these conclusions. He said that yes, there is a positive charge, right? And he knew it was positive because he was working with those alpha beams that were also positive. So he knew that when those alpha beams, that positive, came in contact with the positive charge, they would be repelled. So there is a positive charge. However, that positive charge is not distributed evenly, but it's actually very, very dense, and it's in a very dense positive core. He said that most of the atom is simply empty space, but it's occupied by those tiny electrons. So rather than having the positive core spread out throughout, instead we've got a very, very, very dense positive core with electrons that are spread out around it. Rutherford called this new model the planetary model because it models our solar system, right? We have our sun in the middle and we have planets orbiting around the outside. So Rutherford said that we've got our positive core in the middle. We now know our positive core is called the nucleus, and those negatives are orbiting around the outside. So this also helped to lead to the discovery of the proton. So now we've got another subatomic particle. We've got another particle smaller than the atom that's living in the atom. But now we know it has a positive charge. So Rutherford's nucleus was actually extremely tiny, only 1/10,000th diameter of the entire atom. So it was very, very small in order for it to pick up. Later, Rutherford actually proved that other atoms contain hydrogen nuclei. So this is kind of confusing to some students. Remember a hydrogen nuclei, if you take a look at hydrogen on the periodic table, hydrogen has when it's charged, it has no electrons. Hydrogen has no neutrons. So hydrogen is actually just made up of one proton. So scientists often use the term hydrogen nuclei. What they're talking about when they say hydrogen nuclei is just a proton. So later, Rutherford was able to go ahead and confirm that it wasn't just gold that had these protons. It was actually other atoms as well too. He later concluded that the simplest positively charged particle, and he named it the proton. So once he went ahead and confirmed that these particles did exist in other things besides gold, he named it the proton, and it was the second subatomic particle that we saw in chemistry. There was an issue of mass, though. So this is the challenge with Rutherford's conclusion. It was a great conclusion. It explained his experiment, but there was this idea of the mass. So protons actually accounted for most of the mass of the atom, right? Protons weigh much more than electrons. Electrons are not very heavy at all. So protons seem to account for most of the mass, but evidence showed that atoms had only half the positive charge that was expected if the nucleus was only composed of protons. So for example, let's say that we know an atom is supposed to be made up of 4 units of 4 protons. So let's go ahead, 4 protons. So based off the weight, an atom should be made up of 4 protons. But scientists were finding that an atom made up of what should be 4 protons only had a charge of positive 2. So essentially, protons weren't accounting for the entire mass. There was an issue between charge and mass. So either the charge was correct and it seemed that we had half the number of protons, or the mass was correct and we had double the number of charge. So the answer from that actually came from another radioactive beam, and that came from James Chadwick. So Chadwick was around in 1932, and he was experimenting with radiation that came from beryllium. This particle actually had no charge. So the radiation he was discovering or was studying had not a positive charge, not a negative charge, but it had a neutral charge. And it also had the same mass of a proton. So Chadwick kind of had this brainstorm and said, hey, this solves the mass problem. Maybe this type of radiation is also, or this particle is also present in atoms. So Chadwick found the last subatomic particle, and he found that that subatomic particle actually carries no charge, but it has the same mass of a proton. Well, a particle that has no charge but the same mass of a proton, we should remember from grade 9, that's called the neutron. So Chadwick actually solved the mass problem. He said that there's both protons and neutrons in that dense core, but neutrons actually don't have a charge, so they're a little bit harder to detect. So let's remind ourselves now where we're at, and let's recap, and let's remind ourselves of the structure of the atom. So now, thanks to Rutherford, we know that there's a proton. We know that proton's in the nucleus, and we say the mass is about 1 AMU, atomic mass unit. We'll talk about this more next class. We know that there's a neutron in the nucleus as well too. That neutron has a neutral charge, and it also has a mass of 1. And we also know that there's electrons. Those electrons are outside of the nucleus. They have a charge of -1, and their mass is actually so small that we don't even register it. We call it nil. It's not quite nothing, but it's significantly smaller than the mass of a neutron and a proton, so it really doesn't add to the mass of an atom. And again, an overview of what we found so far. We started with Democritus. Democritus was those indestructible particles called atoms. Then we moved on to Dalton. Dalton took what we knew about chemistry at the time and developed the billiard ball model. So he actually described the shape of these atoms and what they look like. Thomson designed the plum pudding model. So Thomson was the first one that discovered electrons. Rutherford had the planetary model, and Rutherford was the first one that introduced the idea of the nucleus and the proton. And then Chadwick was the one that actually discovered neutrons through radiation from beryllium. So this is kind of where we're at now. Now we're up to about 1932. So now we're going to take a look at the theory that you have been using up until now. So we're going to take a look at the last discovery and how that led to the theory that you've been using up until now, and the theory that you're going to continue on with grade 11. So in order to look at this, we have to look at our modern discoveries. And our modern discoveries are from both Bohr and this idea of this guy called Schrödinger. So before we look at what Bohr did, let's look at some of the challenges with Rutherford's theory. So we know that there's a mass problem, but there was also two other things that couldn't be explained based off of Rutherford's theory. The first was the stability of the atom. So a charged electron orbiting a charged nucleus should actually lose energy as it orbits. So the idea is that an electron couldn't indefinitely go around. It should eventually lose energy, and crash into that nucleus. So based off of just the idea that electrons are floating wherever they want, the atom wouldn't be stable. There was also the line spectrum of elements. I'm going to show you a picture of this in a second. The idea here is that all elements have a unique signature color when excited. It's almost like a fingerprint, and the fact that electrons are just existing kind of wherever they want doesn't help to explain why each element looks different when you look at its line spectra. So this is what we mean by a line spectra. When an element releases energy, it has a unique fingerprint of these lines. So hydrogen is going to release a line that's about 400, and we'll call that 10 nanometers, purple line. You have this blue line, you have this green line, and this kind of orangey reddy line. So this is hydrogen's fingerprint. Mercury looks like this, neon looks like this. So each one is unique. How does each element release a unique line spectra when the electrons can exist wherever they want? So Rutherford's planetary model couldn't explain this. Bohr actually studied these line spectra, and he was able to add to the modern theory. So Bohr understood that the 4 visible and invisible emission lines of hydrogen corresponded to specific jumps in energy levels. So what Bohr said is that these lines, these energy lines here, represent electrons actually jumping from energy levels. So an electron jumping from this level to this level is going to cause that line. An electron jumping maybe from this level to this level is going to cause that line there. So each of these distinct lines look that way. They're distinct, and they're caused by electrons jumping from one level to another. So Rutherford said that electrons just exist wherever. They're just kind of orbiting wherever they want. Whereas Bohr said, well, no, they don't exist wherever. They must exist in these specific, he called them energy levels. So we know that we draw our energy levels like this. They're like rings that go around an electron, around a nucleus. And we know that the electrons, terrible drawing, have to exist somewhere on those distinct energy levels. And the jump from different energy levels is what's actually showing these line spectra here. All right. So to recap, electrons, based on what Bohr said, can only exist at a specific orbit or energy level around the nucleus. This led to the creation of Bohr's shell model, and there was 3 points to Bohr's shell model. So you remember those rings around the nucleus in grade 9? We might have called them shells as well too. That was based off of one of Bohr's terms. So Bohr said that electrons can only occupy certain discrete orbits or energy levels. So again, an electron can be in the first orbit or the second orbit or the third orbit, but it cannot be anywhere in between. Electrons can exist in an energy level without losing energy. So that helps to explain the stability of an atom. So an electron can exist in this first energy level or the second energy level. It can be comfortable and it's not going to lose any energy. Electrons absorb or release energy only when they change energy levels. So an electron is allowed to jump from the first shell to the second shell as long as there's room. It can jump from the first shell to the second shell, but it's going to require energy. So every shell you take a step up, it's going to require energy. So to go from the first shell to the second shell, energy is going to be required. On the other side of that, you can fall, right? You can become less excited from the third shell to the second shell as long as there's room. And if you do so, you're going to go ahead and you're going to lose energy. So it's going to require energy to go up, and you're going to release energy when you go down. All right. So a little bit about Bohr's electron arrangement then. Bohr's orbits or energy levels actually had a fixed number of electrons. So you can't have infinite number of electrons existing in the first shell, and you can't have an infinite number of electrons existing in the second shell. There was actually specific numbers. So in the first shell, you can only have 2 electrons. In the second shell, you can have a maximum of 8. In the third shell, a maximum of 8. And these numbers kind of remind you a little bit of grade 9 Bohr-Rutherford diagrams. So we've actually got ourselves to the Bohr-Rutherford diagram, and the Bohr-Rutherford diagram is what we are going to continue to use this year. Just a reminder, when an inner orbit is filled, electrons must occupy orbits further from the nucleus. So essentially that means when that first ring is full, you then go to the second ring. When that second ring is full, you go to the third ring. And when you go to the third ring, you would go to a fourth ring, and so on and so forth. Cool thing that we're going to learn, and we're going to start talking about this in about 2 lessons. Bohr's shell model actually explains the structure of the periodic table. So I'm going to come back to this later, but it explains why the periodic table isn't just a grid, why it has such a unique shape, and the periodic table was actually defined before Bohr's shell model. So it actually went back and explained this theory. So that's how Bohr kind of knew that he was on the right track, or he was much closer to being right. Of course, there's a problem with Bohr's theory, and the problem with Bohr's theory is that Bohr's theory actually only really describes the hydrogen atom, and it really doesn't apply for much more than that. So this leads to our modern atomic theory, and that modern atomic theory is from Schrödinger. Now, I like to introduce this modern atomic theory now. You're not actually going to be using it until grade 12. So in grade 12, the very first thing I'm going to do is I'm going to teach you this new atomic theory, but I want to introduce it to you right now because because I don't want you to get too comfortable with Bohr-Rutherford diagrams. I don't want you to think that they're the end-all be-all. They answer all of our questions that we're going to have in grade 11 chemistry, so we're not going to bother teaching you something new yet. But there are quite a few flaws with the Bohr-Rutherford diagram. So Schrodinger actually used physics, and he used the wave equation to describe atoms in terms of energy. So he looked at atoms more so in terms of energy. He looked at it more from a physics end. So he was really interested in tracking the location of electrons. He found that electrons are actually traveling extremely fast. So the more you know about an electron's speed, the less you know about its location. And the more you know about its location, the less you know about its speed. So he said that electrons are actually so fast, we really can't tell where they are. So electrons actually then don't exist in those 2D orbits. They more so exist in a 3D cloud, which just makes sense, right? You have an atom, and an atom's actually going to be 3D. It's not 2D. So it's not going to be stuck on this little 2D orbit. It's instead going to exist in a 3D cloud. Electron clouds, therefore, are arranged around the nucleus, not those little shells. And the exact location of an electron is not necessarily known. So next year, we're going to go ahead and we're going to show you this electron cloud model or electron configuration, and it's going to help to answer a lot of questions that you might have this year about the theory of the atom. So just kind of an idea of what they look like. We have a bunch of clouds of an electron. So we have the nucleus is here, and we have a cloud that might look like this, a nice big circle. We have a cloud that looks like this, a nice barbell. We have a cloud that might look like this, a sideways barbell. All of these will actually stack on top of each other, and they're going to form this 3D atom. So each electron does have a little 3D space in which it can go ahead and it can occupy, and all of these 3D spaces stack on top of each other, and they're going to form that 3D atom that we're going to study next year. So look forward to talking about Schrodinger more and wave equations next year. This year, we're just going to stick to good old-fashioned Bohr-Rutherford diagrams, but now you kind of know how they came to be. So now that we understand Bohr-Rutherford diagrams, why don't we move on to our first new topic? And our first new topic we're going to talk about is going to be isotopes. So join me in the next video when we talk about isotopes.